All right, so now we're going to talk about the ANOVA, which is the analysis of variance. The ANOVA is an absolute fabulous tool, simply because there are things that are associated with the t-test that create some difficulties when doing analysis. So with the t-test, you can only generally compare two means. You cannot compare multiple means simultaneously. You would have to do that separately in separate t-test. You can also only have one predictor, one independent variable, which sometimes you might have more than one. And when you do end up actually running those multiple t-tests, you increase the probability of a type 1 error, which is really not the intention of what we want to run. We want to have a 95% level of confidence, which means a 5% error. If we're going to run multiple t-tests, we're going to take that 5% error and start to increase it very rapidly, almost exponentially. So the ANOVA takes a lot of those limitations and removes them. First of all, we can compare several means. So if you had 8 or 9 experimental elements that you wanted to compare to a control, you could compare them simultaneously. You can also have more than one independent variable. And ANOVA is generally thought of an extension of regression, which is why it's called the General Linear Model, GLM1. That's what that means. So it's just another version of regression, essentially. All right, so let's talk about what happens when we run multiple t-tests. So in this example, we're going to have 3 different experimental conditions. We want to run comparisons between those. The comparisons that we're going to run is 1 versus 2, 1 versus 3, and then 2 versus 3. So we would have to run 3 separate t-tests. So the probability of our type 1 errors would be then our 0.95, which is our level of confidence that we always use for engineering, raised to the 3rd power because 3 is a number of comparisons that we're running. So the level of confidence drops from 0.95 to 0.857, which means that increases our probability from 5% to 14.3% of making a type 1 error. I don't know about you, but that's not exactly desirable. So that we call this a family-wise error. And we're going to talk about when we do ANOVAs and we're doing post-hoc tests, we're actually going to be making these calculations to determine exactly what level that we want ANOVA to run the calculations. All right, so ANOVA, it's generally just a null hypothesis that the means are the same. It's exactly what the t-test runs. So the null hypothesis is very much the same, except the ANOVA is what we call an omnibus test because it's not testing for the exact differences between any of those means. It's just asking and testing for what is the overall difference between all of the groups. So it's simply going to just tell us that the group means are different. So if you're comparing 2 group means, that's fine, they're different. But if you've got 6 or 7 group means that you're looking at, you don't know which one of those 6 or 7 are similar or which one of those are different. And that is really, when you're running multiple means, you really want to be able to identify which of those 6 or 7 elements that you're looking at is indeed the different element. Because if you're running different types of manipulations, you want to know which manipulation is best. In terms of regression, we already used the ANOVA to look at whether or not the model was good at predicting an outcome, essentially whether or not it was better than the mean. When we look at experiments, which is what we're going to be doing from here on out with the ANOVA, we're trying to find out which experimental manipulation led to differences in performance. Hopefully, we have these manipulations set up so that we can increase or improve performance. So essentially, we're asking the same question between regression and experiments, but in experiments, it's more of a systematic manipulation, which we don't have in regression. Regression is just, is it good or not? Is it better than the mean or not? So the ANOVA in experiments is a little bit stronger because of that systematic manipulation. All right, we're going to talk a little bit about the theory of ANOVA because it is important to understand all the elements so that you can interpret the output a little bit better. So how much variable is there between the scores? is measured by the total sum of squares, or SST. How much can be explained by the model? That's our systematic variation. That is our model sum of squares. And how much variability cannot be explained? That would be our unsystematic variation, or our residual sum of squares. Again, residual is associated with error, cannot be explained. That would be the error in the model, so that's why that's SSR, unsystematic variation. All right, so the amount of variability that we have in the model, we're going to compare that to the error in the model through the use of an F ratio. If the model can explain more variability, that means that the manipulation did have a significant impact on the outcome. So that is what we want, and we're going to be able to figure out how that F ratio works. So if the experiment was successful, we're going to be able to say that we've had more explained variance than non-explained variance, so more explained systematic than non-explained unsystematic, which will essentially mean that the SSM, or our model sum of squares, will be greater than our SSR, or our residual sum of squares. All right, now the ANOVA does also have some assumptions, very similar to every other test that we've talked about before, but thankfully most of them are fairly easy assumptions to handle, similar to the t-test. So our data must be independent. We cannot run dependent data in an ANOVA. The dependent variable has to be measured on an interval scale. The variances must be similar for each experimental condition. That's the homogeneity of variances. And we have to have some type of a normal distribution. Good news, ANOVA is fairly robust. So even if you do violate the assumptions, the F ratio will generally still be accurate. Now that is a little bit of an oversimplification, and we're going to get into more details about that here in the next slide. But that is very important to know, that we can still violate some of those assumptions and not have to throw away the ANOVA test. So what happens when we violate some of these assumptions? If we have equal sample sizes or unequal sample sizes, really going to depend upon how our assumptions are handled. So if we have equal sample sizes, no issues with anything. The F statistic is robust to violations of normality. It's also robust to violations of homogeneous variances. So if you have equal sample sizes, it doesn't matter what your data set is. You can use the ANOVA at will. If you have unequal sample sizes, that's where things get a little bit different. The F statistic is biased when normality is violated, but only in one direction, essentially just if it's skewed. If your data has kurtosis, it's usually not a problem. So it only is a problem if your data is severely skewed, or skewed where your z-score statistic is greater than that 1.96. It's also not robust to violations of homogeneous variances. However, we do have a fix for that as well, which we're going to get to in a few seconds here. If we have groups that have larger sample sizes, and those larger sample size, the larger sample size has the larger variance, then the F ratio is fairly decent, and we're more likely to get a non-significant result when a significant result really does exist. If the larger sample size has smaller variances, then we're probably going to be able to see a significant result when no difference exists. All right, so that can be a little bit confusing, but again, we can solve this variance issue very easily. So there are two different types of modifications to the ANOVA, the Brown and the Forsyth and the Welch's ratio. They both control power pretty well. I would say that you're probably going to always want to use Welch's because it has a very, very good power when we have extreme means with large variances. So when you want to run the ANOVA, you're always going to want to run the Welch's just in case your homogeneous variances turn out to be significantly different. Now we're going to do ANOVA by hand, go through it pretty quickly, but just want to get you an idea of where all this information is actually generated from. So we're going to look at Zicam on sickness. You can either take a sugar pill, which is nothing. You can take Zicam, which is supposed to reduce the levels of your illness, but you're going to have missed doses, and then you can be the person that takes Zicam very consistently. And then we can compare that to an objective measurement of your sickness. So here's our data, and what you can go ahead and see by our data, we have the mean and the standard deviations for each of our data sets, and we also have the variance, forgot about that. But we also have this grand mean, grand standard deviation, and grand variance. This is in relationship to the entire data set. So this is the entire data set, and that's why we call it the grand. And we're going to need that data if we're going to run this by hand. Again, thankfully you're going to be using SPSS, so you're probably never going to have to run this by hand, but it's pretty simple to actually do it by hand if you had to. So here's just a look at our data. We have our grand mean, which is right here, that line, and then the mean of the 3 sets of data. So the total sum of squares is we are taking the difference between each data point and the grand mean. So each data point to the grand mean, that is what we're going to do, and we're going to take and sum those squares. So here's the calculations to go ahead and do that. The degrees of freedom, because we used one element, we used the grand mean to calculate the differences, that's where that 1 comes from. So the degrees of freedom is just simply n minus 1, so we have 14. And then we have our model sum of squares, so that's where we take the mean of each data set, which is the green, blue, and the red lines, the mean of the data set minus the grand mean, and those are the calculations for that. Now, how many degrees of freedoms do we have? We used 3 means. So 3 minus 1 will have 2 degrees of freedom for the model sum of squares. All right, the residual sum of squares, again, is the error. So we have the mean of each data set, and we're going to take the difference between the data point and that mean. So that gives us the error associated with each group. And those are the calculations to create the residual sum of squares. And then how many degrees of freedom did we have? We had 5 data points, minus 1 was the mean. So 5 minus 1, we add that up 3 times, we get 12 degrees of freedom for the residual sum of squares. All right, we should be able to say that our total sum of squares is equal to our model sum of squares plus the residual sum of squares, which indeed turns out. And we can say the same thing for the degrees of freedom. The total degrees of freedom should be equal to the model degrees of freedom plus the residual degrees of freedom, which is true, so at least our math works out. We can also calculate the mean squared error and the residual squared error, so the MSM and the MSR, and then calculate the F ratio. So this should be very similar to what we talked about when we were doing a regression. And then we construct our summary table. So now we have our F is 5.12, that asterisk indicates it's significant. How did we find out it's significant? Well, if the value is greater than 1, so if F is greater than 1, we know that the experimental manipulation had some effect. So we want F to be greater than 1. But it doesn't tell us whether or not it's statistically significant. So how do we find out whether it's statistically significant? We're going to have to compare that with statistical tables. And ANOVA, or the SPSS, actually does that for you, so you don't need to worry about it. And you're going to compare the 2 and the 12 degrees of freedom on the statistical table. And you find out that at 95% level of confidence, it's a 3.89. 5.12 is greater than 3.89, so we do have a significant difference. All right, we're going to do that again on SPSS and do some follow-up tests, because we need follow-up tests to be able to tell us whether or not the experiment was successful. We know that the group means are different, but we don't know if the placebo is different than the regular, or is it the missed dose versus the placebo, or is it the missed dose versus the regular? We don't know which one of those elements is better, so we can't tell anybody you should be taking this medicine when you have a cold because you'll get better faster. We don't know. We just know that one of them is different. The placebo could actually turn out to be the best of the three. So we're going to have to run some additional tests to find out where those differences actually do lie. All right, a couple different types of follow-up tests that we could do. One we're never going to do. We're never going to be running multiple t-tests. That's just a bad idea. We could run contrast, and those are hypothesis-driven. We're going to have to figure out those beforehand. We could also run some post-hoc tests. So we have no hypothesis. We're just throwing everything at the wall and trying to see what comes out. And we could also do a trend analysis. We're not really going to get into trend analysis because we don't do that too much, but we do the other two quite frequently. So let's talk about contrast. So we want to be able to figure out how much variability is actually explained by the model. So we're going to break down our hypothesis to figure out which groups do we think would differ. Now there's some rules when choosing contrast, so you have to think about these before, because these things all have to be determined a priori, so that's before you run the test. So these are elements that we have to consider before we actually figure out what contrast we're going to select. Contrasts must not interfere with each other, so they must be unique. You can only look at essentially two chunks of data, or two variations. And you always have to have one less contrast than the number of groups. So in our example, we had the placebo, the missed dose, and the regular dose. We had three groups, so 3 minus 1 is 2. We can have maximum of 2 contrasts to be tested. So how do you choose a contrast? Well, most of the time you're going to have essentially one control group, and then you want to compare that control group to something else. So that is really how you're going to dictate how you set up the comparison between what is not controlled or what is controlled and what is manipulated. So the first contrast is always going to be, say, we're going to compare our control group with any experimental condition. And if there's no difference between the experimental conditions and the control group, your experiment has essentially failed.